Hello all. I will be talking about the industrial acceptance of open hardware and why this kind of a topic is that the RISC-V has really been kind of like a true enabler in decades for this kind of phenomenon to actually be fueled again. But I'll be anyway talking a little bit about the opportunities of course are there, but also risk challenges and what is needed, what it is to make commercial chips. So like Jari described, I have quite long background in working in the industry, and lately also from my professor of practice job, we created the SOC Hub, which is exactly trying to or looking into the commercialization of the open hardware, trying to kind of like harden the open hardware to industrial level, and then we will be publishing our results about that and so on. So here you can see agenda. I tend to like to talk about the markets a bit because it gives you the context what we are talking about. Then about RISC-V and a little bit about the SOC Hub and what we are doing in the end. And there is a layout of a chip that we made a while ago. So the key topics, some observations. These are to guide you through my talk. So what you will be expecting, what we will be talking about, these are the questions that you could think of when listening. And well, RISC-V overall, a lot of initiatives, a lot of funding around creating RISC-Vs. Many large semiconductor companies are backing up RISC-V. They want alternatives, they want competition, they want to have a choice compared to, for instance, ARM, which is very successful in providing the mobile cores, for example. A big thing, the software flows. Already now, RISC-V is successful. You can see it because they are getting industrialized. They are getting included into the chips of the big SoC makers. But what it will take to kind of like have the next step with the open hardware overall for the RISC-V, but also surroundings. Today, if you look on the market, and I think that's since we have been developing the RISC-V for years. If you check the market, and if the market acceptance is there, you can see cores, and that's there. So RISC-V cores are there, but you can see that they are mostly in the lower performance, this kind of in-house cores where they handle some kind of support or control functions, and not as the main CPUs. Those are still populated by the ARMs. There is a performance gap likely that is causing that, and a lot of the RISC-V is focusing on the core development itself, basically instead of thinking about the SoC concepts as a whole. And then you can see some risks which we will be talking through later. A bit of the market first to get the kind of like understanding where we are, where are the big companies. So you can see from the middle picture, basically, the United States, obviously very large, and China getting a lot of market share, which is significant because China is big kind of like RISC-V contributor today. So most the chips that have RISC-Vs actually as the main CPU tend to emerge from China mostly. Of course, this has to do with the geopolitical things and such also. But anyway, you all probably know also the EU's Chips Act and the realization that we need to in Europe also start to invest heavily into the chips, and that's partially the reason. The biggest companies doing, or fabless companies doing the ICs without the fabs, they are basically based in US and Asia. And a little bit about the market sizes. So like I just mentioned, the RISC-V development is mostly focused on the IP core development instead of the SoC. And if you check basically the market, the IP market, it's the addressable market is roughly like 5 billion. This is not from this year, but a couple of years ago, so a little bit adjustment. And the market for making the chips, well, it includes foundries, but anyway, it's in the range of 500 billion. So making of the SOCs is where you make the most of the money in this industry, even though the IP market is big, but then it's kind of like pretty much dominated by the top 3 players, and many don't know the kind of like companies after the top 10. All right, and for the RISC-V itself, so I don't know if it's obvious to everybody, but actually we tend to develop the cores, but the a big thing is actually the software and the tool support. So this is a figure that tries to depict the development cost of a SoC with all the factors that there are. It's a little bit on the high side, so never mind the absolute sums, but it gives a figure that where do you spend the money. And actually, if you think about the kind of like RTL design, it's a little bit smallish if you compare it to the verification and software development. But in RISC-V, we have the software chains, tool chains, the libraries, etc., which allow us to develop and innovate in the core architecture. And that's the key driver to keep the software flows in such shape that it is forever, so that anybody could actually design a CPU core, try to make it better than the competitor, etc. That's really, like, at least from my point of view, a key thing in the RISC-V ecosystem. Then I have actually a couple of slides about the where do you actually spend the cost of a SoC development. So again, you can see here that the SoC design is 20%. It expects that you actually developing something new. You are not just putting some IPs in. The IPs today they are expected to be very kind of like good to be integrated, so that you don't need to do much of development to have them integrated into your chip, so that you actually spend quite a small amount of money for the IP integration, that kind of thing. So it means that, for instance, if you would like to use the open hardware, probably you would need to spend a lot more money on the IP qualification than when you buy it from the kind of like market ready-made. And there is a lot of things that are in these different boxes. You can all read, so I don't go these through, but kind of like giving a picture that where do you actually spend the money? Software, physical design, verification, and the design. That's the biggest things. And what ARM said, so they are also very aware of RISC-V, and this is from their blog, but it's true for also the RISC-V. So this is exactly what RISC-V also needs to address, because the if you have a good ecosystem and you have the software, you have reusable verification, you have the tools, etc., you can just kind of focus on putting things together and focus on the key thing that you want to do, your own algorithms or IPs that you want to bring in to the chip, instead of kind of like building the infrastructure of the chips, etc. And again, here especially you can see the software development and test tooling, which is where a lot can be benefit from the ecosystem. And that's typically because it's somehow easier to open source the software and test rather than your hardware. It tends to be your kind of like competitive differentiator. And well, you probably are aware of the RISC-V ecosystem. A lot of open source, but also a lot of commercial software and commercial cores. and the here in the in-house corner you have NVIDIA, you have also likes of Western Digital, Seagate, etc. And this is increasing all the time. And what the RISC-V Foundation actually does, it's the ISA specification and these compliance things, and trying to kind of like keep the ecosystem together so that it doesn't start to deviate. And a little bit about that later also. Couple of examples of the chips. So like said, there ain't too many RISC-V based chips that you can actually go and buy. Here are a couple of examples. So Renesas just a while ago, they published that they will be bringing on this RZ5 chip, which is low-end lineup of the 64-bit processors they have. So having Andes core 64-bit RISC-V. From China we have Star 5, that is who are producing this JH7110 SoC, and then for the microchip FPGA maker, they have this PolarFire SoC that has 4 cores from the C5 as the main application CPUs there. So they are using commercial IPs, and that's it's a kind of like a little bit thinking, because you have a lot of open hardware available, like said there, a lot of open source cores, but then the commercial makers actually tend to choose the commercial cores anyway, so there must be a reason for that, and you might actually guess it already. So what you actually typically need when you want to integrate an IP, and this is for the commercial IP and this is for the open source IPs, but and maybe the, or not always, the commercial ones don't either have all that is required. So the customer, of course, needs the RTL. Sometimes it's encrypted or non-encrypted. Sometimes you don't have the RTL, you just have the design macro. You can have it kind of like part of your chip. Then you can have a model, and then it's integrated in the fab. But somehow you, of course, need the design itself. Then you need the specification, tool scripts, constraints, metadata. If you do, for instance, HiPEAC-based integration, you need something where how you can verify that the core actually functions correctly in the SoC itself. So integration verification suite, technical support is practically always required, especially when you deal with big companies. They would expect that if they run into certain kind of a problem, and they always run into the problems, there is somebody that you can contact and need you, who can help you to have it through. Then training, especially if you have more complicated cores, what kind of bus accesses, for instance, the core is able to put out, and so on. And the software drivers, libs. There is a lot of small box or similar box, but software is of course a big part, at least drivers for a hardware accelerator. And then of course also internally you have more. That's your IP, it's your kind of like key thing. So you want to keep something with you. And this is what, in my opinion, in typical RISC-V or open source hardware is the situation. We develop RTL, and that's the focus, and it's in fairly good shape. And the in general design verification, as said here, it's typically also, at least on the most kind of like used cores, it's pretty okay. Sometimes you are missing the hard things, so the like corner case where you typically nowadays would run constraint random verification and these kind of things. Then when we go forward, if you have memories, and typically the cores have memories, you would need to have to model the memories somehow. You need to have that. Those are technology dependent cells. You might have latches for the register file, etc. This start to be tricky in the delivery. Specification in the open source area, it's actually quite often lacking the details. There are specifications, but maybe not to the level that they are enough for the SoC integration. And this is where we are different from the software, because the hardware doesn't practically allow bugs. If we leave a bug in our chip, it's a huge thing. It's not only that it costs like millions, it's because it takes time to fix it. And in our industry, if you find a bug, then if it's a big kind of a bug where you need to start to rerun your backend, it takes like 3 months, well, 2 to 3 months to have it fixed. Then you need to go hold the manufacturing and testing cycle again. So at least half a year is spent on fixing the bug after you have actually found it and debugged it and so on. So the bugs are extremely costly in our market, and that's the main difference that we have compared to software. And that's why also I think in the open source world, we are not that far in hardware that we are in the software. A little bit about that also later still. Tool scripts, constraints, metadata. This we start to have quite a good amount of designs that have been synthesized. So you tend to have synthesized scripts or constraints and tool scripts for the synthesis tools. But of course, you need to run the whole flow through to have it actually in the chip. So you need to have the layout and clock tree synthesis and whatever. And those kind of flows would be typically missing. Integration verification, technical support not really covered. In training, we are seeing more and more webinars, and this is a good thing because it shares the knowledge much better than it used to be when we only had the conferences to talk about things or people presented things. So we are this digitalization of things is helping us here. Software, especially in the RISC-V, it's really, like I said many times, a very good thing. And then when we are talking about the commercial grade IPs, it's typically that you need a test chip to be able to sell it, so that you have actually proven in silicon that it works. And there are also many times in academia test chips, but not too often, and very often the test chips are quite limited. So again, in the industry, you mostly sell SoCs that have many type of different interfaces and IPs, not just the CPU itself. But it's difficult in academia, of course, sometimes to create this kind of SoCs that are close where the industry is actually going. And when you start to work on the SoC level, you are actually exposed to different kind of problems that would be covered with the test chips. And then the IP protection measures, this for the open hardware, not maybe needed because it's open. But anyway, when you are buying a commercial IP, of course, you may need to have protection for your IP in order to be sure that your IP don't fly to wrong hands. And then the business model. So on the right-hand side, you can see the ARM. So typically you have if you want to have the commercial IP, you have the license fee. And it means that you need to pay a certain amount of money that you get the IP that you can integrate in your chip. And there are multiple levels of that. You can kind of like have a RTL model that you can integrate, but then you can also have this kind of a license which allows you to manufacture and to modify the contents of the file. Of course, you can assume the responsibility of the modifications, but anyway, there are different types of licenses, then royalties. So whenever you sell a chip where with the IP you get a royalty, certain small amount of payment, and this is of course a very good model because it gives you constant revenue source. The chips are typically sold even like 10 years or maybe more. So it's a constant revenue. It's very good. The problem with the IP business is, as well as in the SOCs, that it takes many years from the start of the development of the IP that you actually start to get some money back in. And this makes it difficult to get in. And the open hardware things can help to accelerate from the business point of view. You have certain starting point and not directly from the scratch. And then services. So more and more we see something that the IP providers can help you to integrate their design or take larger portions of your chip, and because they know what they're doing, they know the IP, they are probably faster than somebody that is first needs to learn what it is and how it works, and then try to put it in. And what I actually see here that the for the RISC-V course, it's typically still this kind of a standard model that you have the license fee, and then you have the block, and then you can use it. But what I think the openness allows, and what we can probably see more, is like what Red Hat was and has been doing with Linux, so that you actually can have this service that somebody who knows very well the open source IPs can sell the service that they customize it for your needs. And this is something that is not really seen today, but likely to develop into that direction. At least I would tend to think so. Yeah, so some of the challenges, not just the CPU. ARM also have very extensive academic packages where you can have access to many of the IPs, but kind of like ARM is typically, many people, all the people know that it has CPUs, many people know about GPUs, but then you also have the interconnect, system control, the security IP, certain peripherals, debug and trace. Debug and trace is very essential to industry, of course, because you are spending a lot of time trying to fix the bugs or locate the bugs. And actually, the better debug and trace capabilities you have, the faster you are going to get the chip into the market, because you are always going to run into the problems that need to be debugged. So kind of like if you think that you would be only, again, in the RISC-V world, for example, focusing on some of the parts here, then there is a lot to be put together still. And kind of like in ARM context, they, for instance, provide reference designs, and reference designs are an excellent way to kind of like learn how things work and have an actual working example how things are put together. And every time when you have an SoC, you have wide variety of the interfaces you need to somehow get out of the chip. You need to get the data in, you need to get the data out. And today you need very high-speed interfaces, which are very tricky. So this is again an example, IMX8 from NXP. So let's say modern times microcontroller, multi-purpose off-the-shelf component. A lot of CPUs, high-performance CPUs, but a lot of different kind of accelerators, audio, multimedia, and a lot of interfaces, because you need to, there are so many different kind of use cases where the SoCs can be put into that you just need to have a lot if you want to have this kind of a general purpose SoC available. And in order for the open hardware to be more and more usable for the kind of like industrial level, we should be continue from the course itself to the SoC area, having the kind of like for the, yeah, the connectivity is very important. AI, of course, today, where we have NVIDIA's NVDLab, for instance, and so on. The problem with the connectivity things is that they need the physical macros, so the transceivers and such, and they are tied to the technology, and they need very deep access to the technology, which is sometimes a bit tricky to get from the technology providers like foundries, and need quite strict licenses to be able to do those, and then you would need to distribute those also. But that's kind of like well, they are needed, but it's a difficult problem to solve. And something also here that you need the tooling and automation to actually be able to put it together. So if we think that if we want to make this kind of a chip in academia, it's a huge exercise. So somehow we need clever tooling that can help us on that. So putting things together, doing the physical things, and so on. So there is a lot of development also in the open tooling that can help to kind of like take the next step. Yeah, the quality I have discussed. So just a few core points. The CPU core itself, complex scenarios, reuse. You want to reuse something that's already available, kind of like at the SOC level. If you do something in the core level, available in the top level, it's essential for the speed. Integration. Typically, for instance, in the RISC-V, the customization, well, it's a benefit. It's also a little bit of a curse, but you need to have very good code quality, modularity, in order to be able to do the customization of the core. More and more nowadays, you need to take into account the security. You need to have secure boot. You need to be sure that you are actually running the software you are intending to be running there. And then the physical design things. So from the well, you tend to think about the critical path and how fast you can synthesize, and that's important thing. And there is a crucial role of the memories also. So how do you connect to the RAMs, for instance, which you can't really predict well if you don't have the technology component actually available. Then the DFT chains, for instance, you need to be able to connect well into the chosen DFT strategy of the chip. You need to be your design needs to be such that it has good DFT coverage, and typically that's the thing if you don't use very let's say complicated or exotic structures with latches and so on. And then also the debug and trace. So if we go back to the NXP chip, you have 8 different cores there, and you like to have the debugging to be like easy between the cores. You will be having cases, for instance, that the cores try to access some peripheral. So you want to, if you have an issue there, you want to be able to trace how the access actually goes from the GPUs, in which order they are in the interconnect before they go to the peripheral and these kind of things. So you need to be able to be kind of like be part of that debug chain so that you can actually do it and the timing of the debug and so on. And what it takes to integrate a RISC-V core. So core is integrated correctly. We don't want to perhaps run complex programs because the core is supposed to be functioning already. You want to be sure that you integrate it, so you focus on the interface. Performance verification, and this is because sometimes in the simulation you have very optimal memories, for instance, but in real life those are not, or the interconnect accesses, so that you can actually reach the performance that you are supposed to reach. And then you need to replace the memories by technology counterparts, and here if the memories are kind of like very deep in the hierarchies, etc., it can be quite time consuming to actually replace them. The special cells need special care, latches, synchronizers, etc. They shouldn't be kind of like just thrown there because it's tricky to try to locate them one by one. So there needs to be some kind of strategy for the special cell replacement. Clocking, reset, and power, they kind of like go hand in hand. If you want to have, and typically you want to have different operating modes, different frequencies, different maybe voltages even, this starts to be very complicated and it needs control there in the core. It needs perhaps PLLs, it needs level shifters, it needs isolation, etc. Then physical design and DFT you obviously need to do. Then if you want to have the CPU as the main processor that boots the chip, then of course you need to create the boot procedure and the boot ROM and make it kind of like, again, industrial acceptable, so that you know what it boots into. So there, if you use some external source, it needs to be very secure. So typically you would want to have chip internal boot ROM that actually does the very initial boots of the chip. So, and then you have the security related functions that you want to either integrate with the core or somewhere in the system, but you need to be sure that in the boot time they actually work. So, and in the boot time, we are discussing the situation when you don't even have the PLLs up and running yet. So when you first time put the powers on, it's kind of like full reset and something starts to tick before you can set up the LPDDR controls or so on. And of course, when the samples come back, you want to wake them up, then you need some software there. But anyway, this if you take a core, there is a lot of things that you actually need to do around it before you can put it in the chip and commercialize it, put it in the kind of like industrial commercial chip. And like I said, unfortunately, this kind of plug and play and trial and error, which is sometimes in the software world, it's possible because you can try whether the libraries actually do something that you want them to do, and then you can take them into use and use them. And if there later happens to be some issue, you can actually fix it, change it, or check it again. But we don't have that kind of luxury in the hardware world. We need to be sure that all the use cases that we may have in future are actually covered today. Yeah, then a little bit about the RISC-V specific problem. So yeah, first of all, SOC hardware lifetime is very long, and the development speed is faster. So with the RTL, we can come up with new features much faster than, well, we have the hardware in the field is replaced. And it gives you some challenges to keep all the tools and software actually up to date if you want to kind of like continue the developing of the software tool chains also for all the chips that are actually in the field. And it typically also happens so that when you have some common standardization body, for instance, and there starts to be more and more members, the speed of standardization starts to get slower. It's slower to get changes, etc. But on the other hand, when you are working in the industry, there is the competition always to be the first one. So this goes to the direction that if somebody has a good core and then you have a customer that needs a new feature, you don't want to perhaps wait for the standardization to come up with the solution in a few years, but you want to do it so that you can be the first and you can win the business. And when there are many competing cases like this, there will be some kind of a clash. And when you are talking about the standardization, you want your solution to be the standardized one if you have already implemented it, and so on. So this can lead tricky situations where the software, or yeah, similar thing with the non-standard extensions as such. So how do you take benefit of these things, but still keeping the software flow such that you can, well, first of all, you can run or compile the same software to different RISC-V cores, but also that you could keep the somewhat expected performance there. And one thing to remember is also that bugs sometimes require, for instance, the compiler is somehow modified so that certain instructions cannot be close to each other. So you can see these kind of things, and it might be that it's true for some core implementation, but not true for some other core implementation. So what you will do, if you have made a commercial chip, you of course want to continue selling that, so then you would need to yourself take care of that software flow, and of course that will be problematic. And over time, if these stack up, it may mean that we are in this kind of similar situation that you kind of have competition, but since the cores are a bit different and you cannot be certain that your software actually works as intended, if you would switch the CPU, you end up using the same vendor CPU all the time, because in the industry the cycles are always fast. You may not have enough time to fix all the technical depths if there is a way to have good enough solution earlier in the market. RISC-V internationally is taking steps to prevent the fragmentation, but I think this is kind of like a big thing to be checked and focused in this area. And bugs. I mentioned bugs in the last slide roughly, just to give the idea that the commercial cores, the kind of like highly verified cores, ARM, Intel, whose main business is to do the cores, even from their verification, the bugs slip through. So they are not all kind of like crucial. Some are, but like for the A72, in 5 years you find 25 documented bugs. In Intel CPU, within 4 years you have 99 spec updates, which are bugs or some other updates. So again, if you think about the open hardware itself, it's kind of like inevitable that you will run into the bugs. And then it's always the question that when that happens, who actually does what? So who first of all tries to find the bug? And if the core has already been developed, so you need to branch it, you need to fix it, you need to verify the fix, and there is a lot of things to do. And actually sometimes the upstream in a fix can be a little bit controversial. If you think about the security breaches, for instance, if you wanted to avoid the meltdown type of security breaches, you compromised your performance. And some of the customers may not want that, and some do require that the security is fixed. Some want that the performance will be allowed still. So how do you handle these kind of controversial things? So yeah, this is also for the open hardware. We haven't seen these being productized that much, that also have a long lifetime, that we would have been seeing these kind of issues. But if we would, this is something that you kind of like need to prepare for. And this typically then would mean that there would be some company that assumes the responsibility of hardening the IP itself, so that there is somebody, for instance, if a big SOC house takes that IP into use, there is somebody that you can call to actually do all this stuff to fix things. So again, it leads to commercial licensing scheme. All right. Then a little bit different topic. So you heard me saying about SOC level things. So that's one of the things why we started the SOC Hub. So today we have not been doing actually the RISC-V based development in the SOC Hub. We have been doing the SOC that includes many different subsystems, many processors, peripherals, etc. I'll show it a little bit later. So we focus on tape out of complex system on chips, where we try to focus on the system level issues, and we try to use everywhere we can open hardware, open software. First thing, for instance, that we realized that if you want to run in high clock frequencies, you need some kind of a frequency synthesizer there, and those are not available open source. So we had a good partner in our industrial partner that developed the PLL for us in order to reach the frequencies over 1 gigahertz, for instance. So we work with the tools, processes. We We have very good relationship with EDA vendors and technology providers. We have been working with the TSMC 22 nanometer ULL so far, and we have many companies working directly with us with the SoC design. We have EDA vendors supporting us and collaborating on webinars, etc. A little bit busy slide, but really like the system on chip idea we have. It's kind of like a block diagram of a chip, trying to abstract it, that we have the hardware cores like the CPU, DSP, MCU, then we have the software parts, and then we have potentially something that we could integrate die to die, so in the same package, but the components being in different dies. So going kind of like the next step to the system on chip level, and definitely you need to handle a lot of the software also there in order to set up actually everything that we can work with the industrial partners. We can access the technologies. We have common environment. There are a lot of agreements that we have actually needed to be made, but this is because the now it's in years the RISC-V has started this open source, let's say, revolution in hardware. It can lead. It's evolving, maybe it's revolving, but it's the cores, the SOC, and the tools. I'll probably go first into the block diagram itself because it might be interesting. So this is the block diagram of the first chip that we did. We wanted to take a few different kind of processors, and we these are from the Pulp platform, of course. So things that are also observed there. These were planned to be somewhat standalone cores, so we needed to do some modifications. We actually made quite some modifications here and there. But anyway, there is a boot processor, a small system control processor that boots the chip. Then we have this kind of a microcontroller that is supposed to handle all the sensors and this kind of low performance stuff. And then we are doing high performance computing subsystem, which is not kind of like fully ready yet. And we are actually scoping the cores that we will be putting into it, because we will be having next samples each year coming from now for the couple of years. We have external connectivity so that we can connect another chip or FPGA, AI accelerator subsystem, the NVDLA, Ethernet, 1 gigabit Ethernet, DSP subsystem, so the TTA open ASIP in a DSP configuration, and then the interconnect. And the chip-to-chip is a block that we needed to develop. Suitable one wasn't in open source at that time, very lightweight. We needed to do a lot of stuff, a lot of development in the interconnect area to have it working. But mostly everything is open source and available. Also in the big thing in the HPC subsystem was the cache system implementation. But this is 15 square millimeters in TSMC 22 nanometer, and you can actually see a lot of system level issues that you will focus on there. And I hope that when we get students and graduates to work on this, you are exposed to such things that the SoC architects actually need to think about. So for instance, the interrupts, they need to be somehow globally controlled and distributed when still having reasonable latency for the interrupts. Then you need to think about the flows, how from which interface you get data and how it's going through the whole chip and so on. and that you have the correct performance in each of the places, especially with the interconnect. So for instance, the interconnect, we have actually many interconnects. So for the most high performance parts, we have the 64-bit interconnects, but lower performance parts, we have 32-bit interconnect, and then we also have for peripherals configuration interconnect in the SOC level itself. And then we developed or did this dev kit. This is a work ongoing type of a figure, because we will be having 3 different chips, and we want to have, if possible, 1 development kit. Well, we need to do another likely, but there are some interfaces that are not in the first version, but are in the next ones. But we are kind of like really developing on top of the chip. It will be packaged, then we put it there, and we distribute this to our companies and partners that they can actually play around with it. And for that, we also need to do the software flow. So I actually skipped this first. We are using Rust software language to create this hardware abstraction layer. So basically the board support package that allows you to easily use all the peripherals that we have there. And in the software world, we also kind of like, it's not evident, but if you take a lot of different open source IPs, the software frameworks, if the software is available, the frameworks at least are different. So you actually need to do quite some work to get the software to play together. And yeah, that's what we do with Rust, which seems to be a good choice. For the top level integration, we intend to use, we are actually developing this still, the HiPEAC tooling. This is because this will, or there are some commercial tools. They are not open source tools much yet, but I have seen that this greatly helps in the integration. We can take this still into the next level. So the key idea is there that you have all the essential information packed together. So you have the like address maps, interconnects, etc. There, and you have the kind of like configurations for the hardware and the headers for software, for instance, so that everything is always in sync. And then also in the top level integration of the new files and version control, etc. It's easier when you don't need to manually handle it. And sometimes, for instance, if we go forward, the next steps would be to define the power intent also. So if you are working with the low power devices, then you will likely run into the UPF, where you need to describe how you will actually create certain power structures of the chip. So keeping it all together and always kind of like all the files up to date, it's essential to be able to handle those kind of big chips like NXP's chip. Was there something else? Probably not here. Yes, and like said, this is our schedule in the SOC Hub. So we made this chip called Ballast, which we are working on the Jackal, and we'll complete this project. It will continue, but this part with the chip called Headshell, and we are working on many workshops and seminars with our partners also. So with Cadence, we had a one-day training of the digital backend flow. With Siemens, we had Catapult high-level synthesis imaging algorithm workshop, and then we have had different kind of trying to put forward the information of making of the SoCs, what it costs actually to harden the core, what it costs actually to make a chip, etc. And then the examples of the chips themselves. So that's it. Thank you.